Welcome to Ask and Learn.
We are given a collection of sets, and we are asked to construct the intersection graph of this collection. In part A, the collection of sets is A1 equals 0, 2, 4, 6, 8, A2 equals 0, 1, 2, 3, 4, A3 equals 1, 3, 5, 7, 9, A4 equals 5, 6, 7, 8, 9, excuse me, and A5 is 0, 1, 8, 9. Now, to find the intersection graph of this collection, we need to find the intersection of the sets in the collection. So we have that first, the intersection of A1 with A2. We see that 0 is in both sets. We have that 2 is in both sets. We have that 4 is in both sets. And that's it. A1 intersect A3. We see that this is the empty set. A1 intersect A4. This contains 6 and 8, so it's non-empty. And A1 intersect A5. This contains 0, 8, and so it's non-empty. And continuing in this way, we have that A2 intersect with A3. We see that 1 is contained in both, 3 is contained in both, and so this is a non-empty set. A2 intersect A4. We see that there are no elements, so this is the empty set. And A2 intersect A5. Zero and 1 are common, so this is not an empty set. Next we have A3 and A4. Five is contained in both sets, 7 is contained in both sets, and 9 is contained in both sets. So this is not empty. A3 intersect A5. 1 is contained in both sets, and 9 is contained in both sets. So this is also non-empty. And finally, A4 intersect A5. 8 is contained in both sets, and 9 is contained in both sets. So this is also non-empty. And so we see that there are only 2 empty intersections between A1 and A3 and A2 and A4. And so if we draw the vertices of the intersection graph, we have that these vertices, if I draw them in black, are going to be A1 through A4. So I'll simply draw a pentagon starting with A1, and then A2, then A3, then A4, and then A5. And we have that A1 and A3 are the only, we have that 1, 3 is not an edge, and we have that 2, 4 is not an edge, but everything else is an edge. So we have 1, 2 is an edge, 1, 4 is an edge, 1, 5 is an edge. We have that 2, 3 is an edge, 2, 5 is an edge. We have that 3, 4 is an edge, 3, 5 is an edge, and 3, 1 is an edge. No, it's not. My mistake. We have that 4, 5 is also an edge. So we get a graph that looks like this. In part B, we're given the collection of sets A1 equals the negative integers, A2 is the even integers, A2 is the integers, A3 is the even integers, A4 is the odd integers, and A5 is the integers mod 3. And so we have that A1 intersect A2. This is going to be the even integers again, or not even integers. This is going to be the negative integers, which is A1. A1 intersect A3. This is the negative integers intersect with the even integers. So this is going to be the negative even integers. So this is -6, -4, -2 up to 0. A1 intersect A4. This is the negative integers intersect with the odd integers. This is just going to be the negative odd integers. So -5, -3, -1. And A1 intersect A5. This is the intersection of the negative integers with the integers mod 3. So this is going to be the negative integers mod 3. So -6, -3, 0. So these are all non-empty intersections. We have that A2 intersect A3. This is the intersection of the integers with the even integers, which is just going to be the even integers again. So A3. We have that A2 intersect with A4 is the integers intersect with the odd integers, which is again just the odd integers. And we have that A2 intersect with A5. Well, A5 is integers mod 3, so this is just going to be A5 again. And we have that A3 intersect A4. This is the even integers intersect with the odd integers, which is the empty set. A3 intersect A5 is the even integers intersected with the integers mod 3. And this is going to be the integers mod 6. So this is going to be ... negative 12, negative 6, 0, 6, 12, and so on. And A4 intersect with A5. This is the odd integers intersected with the integers mod 3. This is going to be, let's see, we have negative 3, 3. This is going to be the integers plus 3 mod 6. So we have integers plus 3 mod 6, a negative 9, negative 3, 3, 9, and so on. So it's non-empty. And so we have that the only empty intersection is A3 and A4. And so if we draw the intersection graph as a pentagon, so we have A1 here, A2 here, A3 here, A4 here, and A5 here. Draw the edges in red. The only edge that should be missing is the edge between 3 and 4. So there's an edge between 1 and 2, there's an edge between 1 and 3, there's an edge between 1 and 4, there's an edge between 1 and 5, there's an edge between 2 and 3, there's an edge between 2 and 4, and an edge between 2 and 5. There's no edge between 3 and 4, there's an edge between 3 and 5, and there's an edge between 4 and 5. So we should get a picture like this. And finally, in part C, we are given the collection of sets A1, which is the set of all x such that x is less than 0, A2, which is the set of all x such that negative 1 is less than x is less than 0, A3, which is the set of all x such that 0 is less than x is less than 1, and A4, which is the set of all x such that negative 1 is less than x is less than 1. A5 is the set of all x such that x is greater than negative 1, and A6 is all real numbers. So we have the intersection of A1 and A2 is going to be a set of all x such that x lies between negative 1 and 0. So this is just A2 again. The intersection of A1 and A3, we have that if x lies in this intersection, it must be less than 0 and also be greater than 0, which is impossible. And so it follows that this is the empty set. A1 intersect A4. If x belongs to this intersection, it means that x must be less than 0 and must lie between negative 1 and 1. This means that x must lie between negative 1 and 0. And this is the same as A2. And A1 intersect A5. If x belongs to this intersection, then x is less than 0, and x must be greater than negative 1. So again, we have that this is the set of x such that negative 1 is less than x is less than 0. And this is again equal to A2. And finally, A1 intersect A6. If x belongs to this intersection, then x must be less than 0, and x must be a real number. So this is simply A1. A2 intersect A3. If x belongs to this intersection, then we have that x lies between negative 1 and 0, and lies between 0 and 1. non-inclusive, but this is impossible, so this is the empty set. It can't be both less than and greater than 0. A2 intersect A4. We have that x would have to lie between -1 and 0 and between -1 and 1, which means x just lies between -1 and 0. So this is the same as A2. A2 intersect A5. We have that x must lie between -1 and 0 and must be greater than -1. This is the same as just A2. X is between -1 and 0. And A2 intersect A6. Since A6 is the real numbers, this is just A2 again. And then A3 intersect A4. We have that x must lie between 0 and 1, and that x lies between -1 and 1. This means that x lies between 0 and 1, so this is just A3. And A3 intersect A5. This means x lies between 0 and 1, and that x must be greater than -1. This just means that x is between 0 and 1, and so it follows that this is A3. And finally, A3 intersect A6 is just going to be A3 again. We have that A4 intersect A5. We have that x must lie between -1 and 1, but it must also be greater than -1. This is just x is between -1 and 1, so this is A4. And we have that A4 intersect with A6 equals A4. And finally, A5 intersect with A6 is going to be A5. And so looking at the list, all these intersections, we see the only empty sets are intersections of 1 and 3, intersection of 2 and 3. So those are the only two empty intersections. So to draw the intersection graph, I'll draw a hexagon. I'm going to need to make some space somewhere. So I'll just draw it down here. The vertices of the hexagon are going to be A1, A2, A3, A4, A5, and A6. And so we know that the only edges that aren't in this graph are going to be 1, 3, and 2, 3. So we have 1, 2 as an edge, which I'll draw in green. 1, 3 is not an edge. 1, 4 is an edge. 1, 5 is an edge. 1, 6 is an edge. 2, 3 is not an edge. 2, 4 is an edge. 2, 5 is an edge. 2, 6 is an edge. 3, 4 is an edge. 3, 5 is an edge. 3, 6 is an edge. 4, 5 is an edge. 4, 6 is an edge. And 5, 6 is an edge. And so we obtain this intersection graph.